right? Now, if you have eddies in present, like the turbulent are present, movement present, right? So your total diffusion, remember, there are two types of diffusion that can take place, your molecular diffusion and eddy diffusion. And we looked at steady state molecular diffusion here, right? So Ja equals to minus DAB dCA over dZ. But that is not the total diffusion. Your total basically is molecular diffusion, which is the one you just saw now, plus the convection term, right? That means the one due to your eddies. Your convection terms is basically is the concentration multiplied by the mass transfer velocity. And how do you calculate your mass transfer velocity? Mass transfer velocity is basically your mass flux over the concentration, right? Your mass flux over the concentration, meaning your total mass flux is basically the mass flux of A plus the mass flux of B, which is Na plus Nb, over the concentration, which is the total Ct, and the mass transfer velocity you get is in terms of unit of meter per second. So what does that tell us, or what does it gives us? It gives us the total diffusion. So your total diffusion equals to Na equals to your Ja plus mass transfer velocity, which is a convection term, C times B V. So your Na basically equals to minus DAB dCA over dZ, plus if I replace these, I can say Ca over Ct multiplied by Na plus Nb. So this is actually the one of the form of equations that you're going to be utilized. You are going to utilize continuously for this course. And that is the diffusion of the bulk of mass in motion. Now, you can write total diffusions in many ways, right? You can write it in terms of mass fraction, and you can also write it in terms of partial pressures, right? So how do you write it for partial pressures? The first thing, you say PV equals nRT. This is the ideal gas law. We all know that, right? And we also know from we can rewrite this thing the way we want, any way we want. So what do you have here? So we can actually rewrite P equals to number of moles of a volume RT, and we can replace the N over B by C. So you can say P equals to CRT. And now if I want to break it down in terms of partial pressure of gases, then I can say that PA equals to CA-RT, and my PT, which is total, is basically CT-RT. So I can basically say my Ca equals to Pa over RT, and that if that is true, I can actually rewrite my dCA equals to 1 over RT dPa. Right? So if that is the case, and if that was my equation here, I can now replace this dCA in terms of dPa over RT, and I can rewrite this whole equation as minus DAB over dA over dZ plus this. See, simple mathematic manipulation, nothing serious. So I just basically use the partial gas, partial pressure of gases relationship to rewrite this whole equation instead of concentration, but rather in terms of pressures. Can you see? So if sometimes you see that instead of concentration, you only are given the pressures, you can actually rewrite the total diffusion in terms of pressure, no problem. Now, let us look at how can we also write it in terms of mole fraction. So the mole fraction XA, right, is basically the partial pressure of A over the total pressure. Do you agree? Do you agree? Yes or no? Guys, yes, all right. So similarly, can I also not say that the mole fraction of XA can also be the concentration of A over the total concentration of because that is the basic definition of fractions. So if these are true, I can rewrite my thing as saying PT multiplied by XA equals to PA, and PT multiplied by DXA equals to DPA, because I'm just basically writing in the form of a derivation. Similarly, I can write CT multiplied by X equals to CA, and I can say DCA equals to CT dXA. And if that is the case, I can rewrite this whole equation again, saying that Na equals to minus dAB PTR over RT, and replace the dP over dz to dxa over dz, and replace this part here by xa multiplied by Na plus Nb. So this total diffusion, you can write the any way that you want. If you want to write it in terms of, if you want to write it in terms of concentration, mass flux, no problem. If you want to write it in terms of partial pressures, no problem. If you want to write it in terms of mole fraction, no problem. You are the one who decide how you want to do. Are you with me? Are you with me?
Yes.
Sure.
All right. So now, before I continue again, let's take a 5 minutes pause and let's answer questions. So far, do you have any questions? Anyone? Do you have any questions or any observations or any comments that you have seen and you want to make? You can still see the screen, right?
No, no, sir.
Okay, fine, no problem. But so far, do you have any question? Guys, if you have questions, say yes, and if you don't, say no. Miss Ali, good to see you. Do you have any question?
No, sir, I don't have any questions.
Miss Ali, Miss Aziz, Lifa, Lifa. Yes, Miss Aziz, I see your hand. Miss Aziz,
So I just wanted to
yes.
ask, what's the difference between diffusion and osmosis, since they are both the difference in concentrations?
That is actually a very good question. That is a very, very good question. What do you think the difference is, Miss Aziz? What do you think? Let's hear your idea first.
Um, Maybe it has to do with, I was thinking of the example of like a tea bag in hot water. I
Hmm.
think that's an example of osmosis, but then an example of diffusion would be like spraying perfume in the air. One burn while the one is closed.
Miss Aziz, you have asked a very good question, and I'm very happy that you are actually thinking at that level. Diffusion and osmosis is basically same thing, right? But there's a difference, as you have given the example. When you have osmosis, right, is also a type of diffusion, right? But it involves the diffusion through a layer of membrane or something semi-permeable like paper. Remember, you have given the example of a tea bag in water. That's actually an example of osmosis. Why? Do you know? Because the tea bag is encapsulated in those bags, isn't it? And when you put it in the deep water, put it in the water, what happens? Your concentration actually permeates through that membrane, right? In a nutshell, that is how an osmosis work, right? In a diffusion, when you spray that bottle, the perfume in air, what happens? The liquid and air vapor basically one or the other gets diffused into each other without need of any membranes or any permeable mechanism. That is a direct molecular diffusion. There's no need of any membrane or any other things. So that is why when you remember when we had the day zero, what did you had? We had reverse osmosis process to desalinate water, isn't it? So how did we desalinate the water? You basically have a membrane. You pump your saline water through that at a high pressure, and you basically separate the water from the salt. With the water basically comes out through a membrane, right? There's a membrane involved, but that is the osmosis process, right? Because there is a membrane involved. So molecular diffusion, there is no permeability any form, right? But for osmosis, you need a form of barrier. You need something that is permeable. Are you with me? Is the
Yes, sir.
is the differences clear to you, Miss Aziz?
Yes, sir.
Thank you. Anybody else? But that was a very good question, Ms. Aziz. Very good question. Any other question? And another thing misunderstand, Miss Aziz, that when you have osmosis basically the flow of particles normally in one direction. Think of it. Basically, you have that saline water coming in a membrane under high pressure. You have a flux, which is basically dissolved water. So in a nutshell, it's basically in one direction. But when you have molecular diffusion, basically the flow of diffusion is everywhere. There are six dimensions or directions. It's everywhere. That is another difference that one can think of. All right, students, if there's no more question, let us continue. Can you see my screen again? Can
Yes,
you
sir.
see okay, good, great. So now modes of diffusion. There are many modes of diffusion. Imagine, say you have a, sometimes I don't know if you remember your mother or grandmother used to put those mothballs in your cupboards. Do you remember in where you put your clothes? So it's like a naphthalene balls, right? You put it inside in your cupboard, and after some time when you come and you see that balls of the naphthalene is gone. Yes or no? Do you remember?
Yes, sir.
So that actually can be an example of a stagnant diffusion, meaning where one is stagnant and other one is basically is diffusing into, right? So when you have a stagnant diffusion is where one component in a gaseous mixture is transported relative to a fixed plane, right? It can be liquid. That means that naphthalene ball is diffusing into the air, right? Into the air. So how do you now calculate the flux of that kind of diffusion? And you start your fundamental equations, which is this, right, in terms of pressure. And if you simplify it and rewrite it, there's no new math involved, nothing new involved. You basically come up with your equation here, which is your Na equals to dAB over RT PT over Z1 minus Z2 ln of PT minus PA2 over PT minus PA1, which is PT is basically your total pressure. PA2 is the pressure of in the second state, and PA1 is the pressure in the first state, meaning from one to the other one, that is diffusing. And Z1 minus Z2 is basically the thickness, the difference between the two, and this is the total pressure. And then you have your DAB, which is the diffusivity coefficient, and your R is the universal gas constant, and T is the temperature. So when you have a stagnant diffusion, that problem that you need to solve, the first thing you do, you write down this equation, or you need to basically write down this because the others one is in terms of derivation. I mean, one you sit and try to solve it yourself, and it's nothing difficult at all. Now let us look at an example. So what do we have here? We have ammonia gas, which is diffusing at a constant rate through a layer of stagnant air, which is 1 millimeter thick. That means your ammonia gas is diffusing at a constant rate through a layer of stagnant air. That means your air is stagnant and the thickness is 1 millimeter. Conditions are such that the gas contains 50% by volume of ammonia at one boundary of the stagnant layer. The ammonia diffusing to the other boundary is quickly absorbed and the concentration is negligible at that plane. So the ammonia diffusing to the other boundary is quickly absorbed and the is negligible at the plane. The temperature is 295 Kelvin and the pressure is atmospheric. the diffusivity of ammonia in air at this condition is 0.18 square centimeter per second. Now estimate the rate of diffusion of ammonia through the layer. So we need to now calculate our rate of diffusion of ammonia through that layer. That basically all we asking you to calculate is your Na. So how do we now go and solve a problem like this? So the first thing first, what do you have? We have ammonia, which is diffusing at a constant rate through a layer of stagnant air, which is 1 millimeter thick, right? And what is and the ammonia diffusing to the other bound quickly absorbed, and the concentration is negligible at that plane. The temperature is given to you as 295 Kelvin. The pressure, that means you have the total pressure, which is atmospheric, 1 atmosphere, and you know the diffusivity of ammonia. So the first thing first, just let us write down the equation that we are going to utilize. So from this equation that we have derived, we saw that when you have a stagnant diffusion, the rate of diffusion Na equals to dEB, so Z PT minus Pa2 over PT minus Pa1. Now the problem that we have is that we don't have the partial pressures. We have the total pressure, but we do not have the partial pressures. But utilizing these relationships here, we can actually, guys, are we in the right track? That means we can utilize the total pressure, and we know that there's 50% ammonia by volume, so we know the fraction. By utilizing those relationships, we can actually calculate the partial pressure. So let's do that. So your PT is 101.3 kilopascal, and your Pa1, which is 50% by volume of ammonia. So and the total pressure is 101.3 kilopascal. So you can say that Pa1 equals to Ya multiplied by PT equals to 0.5 multiplied by that, and that gives you 50.65 kilopascal. But then I am saying that my Pa2 equals to 0. Why? Because I'm saying the ammonia diffusing to the other boundary is quickly absorbed and the concentration is negligible. It means it is not causing any difference in anything, right? That means like you can say that molar fraction is 0. If mole fraction is 0, then you can say Pa2 equals to 0 multiplied by that, also gonna give you 0. Yes or no? Guys, do you understand what I'm saying?
Yes, sir.
Good.
Sir, can you please repeat that?
Sure, no problem. So if you read the question says that let's look at the scenario. You have ammonia gas, right? You have ammonia gas, and your ammonia gas is diffusing at a constant rate through a layer of stagnant air, meaning your air on top of ammonia gas is not moving at all, it's just stagnant. Now, so what is happening? You have something called stagnant diffusion, meaning one is diffusing to the other one where there's no movement, there's stagnant. Where state 1 before the diffusion, and you know that there's only 50% ammonia there, and the rest can be air, the rest can be water, I don't know, it can be anything, right? But I only know that there's only 50% of whatever in the ammonia, there's only 50% is ammonia. Now the question is saying is that the ammonia is diffusing to the other boundary of the air, is quickly absorbed, and the concentration is negligible. Meaning, once the ammonia has been diffused, it's absorbed, and it's more, the concentration there, once it's absorbed, is negligible. Meaning, the molar fraction there is 0%, right? If the molar fraction is the 0%, then I can say, okay, fine. Does it make sense? Did I answer your question? Did I make it clear for you? Thank you. Now, the delta Z, which is the Z2 minus Z1, it was given to you already because it was given as, where is that now? it was given to you as 1 millimeter already, so you know the difference in thickness of the thingy. It's 1 millimeter, and it's 1 times 10 to the power minus 3 meter. Everything must be that. And your R is, of course, it's universal gas constant, 8.314 kilojoules per kilomole Kelvin. Your temperature T is equals to 298 Kelvin. That is given to you already. How do you know? Okay, the temperature that is given to you is not 298 Kelvin. No, this temperature 298 Kelvin, right? That is how much? 25 degrees Celsius. So, and your diffusivity DAV is 0.18 square centimeter per second. That gives you 1.8 times 10 to the power minus 5 meter square per second. And if you plug in all the numbers, you should be able to get your answer. Can somebody plug in the numbers for me quickly? Please. Are you doing it? Please plug in the number for me and let me know how much you get. Then I can see if my answer and your answer is correct. Please use 295, not 298, please. And I want to know the unit that you get.
Sorry, sir.
Yes.
Could you please go back to the slide?
Can you see my slides?
Yes, I can.
Go ahead.
I just doing it.
Okay, I'm sure.
Yeah.
Okay, so I need to go to the slide, right? There. Can you see?
Yes, I can see.
Okay. So please, when you use the temperature, don't use 298. I made a mistake here. Please use 295. And also, please give me the unit that you get. Answer. Get the answer. Anyone? Miss Aziz, are you doing it? Lifa? Yes.
I have the answer. I'm not sure about the units.
Why? Plug in the units and see which one crosses out and which one you left behind. Which one you left behind. Lifa?
Still working the units, sir.
Okay. Miss Ali?
So I got a very small number.
Tell me.
5.15 times 10 to the power minus 7.
-7.
Yeah.
And unit?
I'm still working out the unit, so
I know why you got the wrong. I got 5.153 times 10 to the -4, not into -7, and I know why you got it wrong. I want to see if you can figure it out.
okay.
What was plugged in the pressure? What value did you put in?
KPI, so
No. So you put in KPA, right?
yeah.
Okay, let's see if maybe mine one is mistaken, but I'll see. Let somebody else do it. And when you did the thickness,
Oh, I put in millimeters.
yep. So you need to change it to meter.
Okay.
Okay, so mine is correct. And get me the unit, please. So the molecular diffusion of flux, you see, is moles per unit area per unit time. That is supposed to be your unit. So the unit that I get, it will be moles per unit time, which is at the kilomoles per meter square second. Are you with me? Can you see my slides still? Guys?
Yes, sir.
Okay. Now, so can we move on? Or do you still want to calculate the molecular diffusion value out first? Guys,
We can carry on, sir.
thank you. So the first, then the one that we just did now was what? Stagnant diffusion, where one component in a gas is trans that we can actually encounter is equimolecular counter diffusion, right? That means the mass transfer rate of two components are equal and opposite. Imagine a box with a moving partitions, right? So when it comes to equimolecular or equimolar counter diffusion, then the rate of diffusion becomes this. Na equals to DAB over RT multiplied by PA1 minus PA2 over Z2 minus Z1. Please write it down for me. For equimolecular counter diffusion, is Na equals to DAB multiplied by PA1 minus PA2 over Z2 minus Z1. And the derivation starts right from the beginning from here, where you have the main fundamental equation of total diffusion. And for equimolecular diffusion, you say NB equals to minus NA. And then if this basically then falls apart, then you're only left with these. And once you solve it, then you get this equation. Do you have it right? Do you have it written down? Guys, do you have it written down?
Yes, sir.
If that is the case, let's look at this example. Example 2 says that air and carbon dioxide mixture at 298 Kelvin and 202.6 has a concentration of carbon dioxide at two planes, 3 millimeter apart, with volumes of 25% and 15% respectively. The diffusivity of carbon dioxide in air at these conditions is 8.2 times 10 to the power minus 6 meters square per second. Calculate the rate of transfer of carbon dioxide across the two planes, assuming first equimolecular counter diffusion, and the second one, diffusion of carbon dioxide through a stagnant layer. So this is a problem with two situation. How do we solve a problem like this? Can you try for 5 minutes, please? Can you try? All right, so I don't hear anything, so let us go through it. So the first one first, what do we have? We have first one is equimolecular counter diffusion, and the second one is asking about diffusion of CO2 through a stagnant air layer. So that means we are going to use two designed equations. But before we can even continue, we need to calculate our partial pressures. So if we want to calculate our partial pressures, let's look at the question. The question says we need to calculate the diffusivity of carbon dioxide is given, right? And air carbon dioxide mixture at 298 Kelvin has a concentration of carbon dioxide at two planes 3 millimeter apart with volumes of 25% and 15% respectively. That means at 25% and 15%. So your total pressure is 202.6 kilopascal. Is twice the atmospheric pressure. So your PA1, the pressure at 1 is YA1 multiplied by the total of partial pressure and 15% carbon dioxide concentration there. So your PA1 is 30.39 kilopascal. Your PA2 is similarly YA2 multiplied by PT gives you 50.65 kilopascal because your concentration is higher there, 25% there. And if it's an equimolecular counter diffusion, we have seen the design equation, which is this, your Na equals to DAB over RT multiplied by PA1 minus PA2 over Z2 minus Z1. So we can write down this equation. Do I have the diffusivity? Yes, 8.26. I know the universal gas constant, which is 8.314. I know the temperature, which is 298 Kelvin, and I also know the Z2 minus Z1, which is 3 millimeter. Is it 3? Was it 3 millimeter? Yes, it was 3 millimeter apart. Sorry, it must not be 3 times 10 to the power minus 6. It must be actually 3 times 10 to the power minus 3. So there is a slight mistake here, guys. Please double check on this. So Z2 minus Z1 is 3 millimeter apart, so it must be 3 times 10 to the power minus 6, not 3 times millimeter to 1000 millimeters 1 millimeter, yeah, 3 times minus 3. And your partial pressure, the difference between the two is 50.65 minus 30.39, and that gives us, we get 2.79 times 10 minus 5 kilomoles per meter square second. And you can see that there is a slight difference between the diffusion flux in each two different cases. So depending on the cases and the situation or the scenario that you have in your hand, you are going to utilize the right proper design equation. Understood? This is of utmost importance that you choose the correct equation to calculate the molecular diffusion. Can somebody confirm that you understand the importance of it? I'm still waiting.
Yes, sir.
Thank you,
Yes,
Difa.
sir.
Thank you very much. Now let me introduce you to all drift factor. Concentration of component A, which is being transferred, is low. The drift factor basically equals to 1. So the drift factor is your total pressure PT over PBM, and your PBM is defined as the logarithmic mean of PB1 and PB2. So your drift factor is equals to PT over PBM, and your PBM is the logarithmic mean of PB1 and PB2. Now, there are various mass transfer actually theories, right? There is two-fold theory, then there is the penetration theory, then you have the random surface renewal theory, and also you have the foam penetration theory. There's many theories actually, and there is still new theories being developed. One of the most commonly used theory is given by Whitman, and this theory is exactly 100 years old. It was developed in 1923. This year is 2023. That means this theory is exactly 100 years old. So what does this theory says? If you look at this drawing, does this drawing remind you of your heat transfer process? The resistance, the drops. Can you see the similarities? So if you have a phase 1, which is this, the gas, you will have a gas form, then you have a liquid form, and then you will have your phase 2, that liquid phase, the concentration there. So that exactly similar to your resistance, the loss of heat transfer through conduction via different resistance, right? Can you see? So there is initially going to have a gas form, then you're going to have a liquid form, and the resistances are here. Rg equals to 1 over kg, and the resistance due to liquid here is again RL equals to 1 over KL, and the thickness here is the total is the thickness of the gas phase and thickness of the liquid form phase, and the diffusivity of gas here is DABG and DABO. The total is your thickness Z, and your flux is moving from this direction to this direction, and that is why you have a concentration gradient here. Can you see? It reminds you of exactly the conduction heat transfer. So what are the assumptions here? The assumptions are that you need to have a steady state system, and you need to also have a laminar layer that exists in each of the two fluids, and resistance to transfer is concentrated in these two laminar layers, meaning here and here, right? Because of the forms. Now, for equimolecular counter diffusion, your Na equals to this, but we have all seen this one. And for partial pressures is basically this equation, and your total thickness Z here is basically the thickness here plus the thickness there. And then the rate of mass transfer per unit area from the gas form is also the similarly from that to that, and the rate of mass transfer per unit area from the liquid form, which is from here onwards, is this, right? So there are additional theories, but we are not interested into too many of the theories. As long as we stick to one, the two-form theory we should know, we should be okay. Now, I mean, we have seen this one already. I have shown you the relationship between the different pressures and the fractions, but still, just recap slightly. What is the relationship between your partial pressure and concentration by Raoult's law and Henry's law? Raoult's law says that a solvent's partial vapor pressure in a solution is equal or identical to the vapor pressure of the pure solvent multiplied by its mole fraction of the solution, meaning your PA equals to PA naught multiplied by the mole fraction, which is the XA, and your PA over PT, this is also equals to this over that, and you can say YA equals to KXA. Yeah, for Henry's law, the amount of gas that is dissolved in a liquid is directly proportional to the partial pressure of that gas above the liquid when the temperature is kept constant, which is this. But in a nutshell, you have different mass transfer coefficients. And if you look at all these coefficients here, your Na equals multiplied by Pa minus Pa1 kg is the individual gas form mass transfer coefficient. You can also say that Na equals to KL Ca1 minus Ca, meaning the difference in concentration, and your KL is the individual liquid form mass transfer coefficient. And you can also say that Na equals to KOG Pa minus Pa pressure. Your KOG is what overall mass transfer coefficient based on the gas phase, and as you go similar to this. But what I'm trying to show here that this is all analogous to whatever you have seen already in heat transfer process. Exactly the same thing. Now, notes to remember is that the inverse of mass transfer coefficient is called the resistance of mass transfer, which is 1 over K. And your gas form control is when the resistance which lies in the gas form, which is this, right, which is this, that is the resistance, and the liquid form resistance equates to 0. So 1 over KOG is equals to 1 over kg. And liquid form control is when the resistance lies in the liquid form, meaning, so your liquid film control is when the resistance is lying here, not there. That is why it's liquid form and it's gas form. We can say that 1 over KOL is equals to 1 over KL because this falls apart. And one thing that you must remember that mass transfer coefficients have different units depending on how it is calculated. It's totally up to you how you want to do that. So I want to end the lecture here for today on introduction to mass transfer. In the next lecture, I'll convective mass transfer, convective mass transfer and so on. Right. So guys, any question so far? I see Lekay has his hand up.
Sir, what does the H stand for?
Which one? That is the hand that is. Let me show you again.
Capital H.
It's a Handy coefficient. You're talking about these, right?
I can't see the slide, sir.
Yeah. It's PA equals to HCA, right?
I can't see the slide, sir.
Okay, let me show you. Just 1 second. Let me just get the slides again. Can you see now?
Yes, that one.
So this is basically a gas constant coefficient. So because this is according so the Henry's law basically states that the amount of gas that is dissolved in the liquid is directly proportional to the partial pressures of the gas above the liquid when the temperature is kept constant, right? So your PA is equals to H multiplied by Ca, so this is constant here, right? So what we are going to do next is we are going to tackle convective mass, we are going to tackle convective convective mass transfer, and convective mass transfer is something similar to convective heat transfer. So we will see a lot of correlations like Schmidt's number, Sherwood's number. That's also coming that we have seen in heat transfer process. All right. So is it is it your new hand or is it a legacy hand?
It's the old one, sir.
Okay, so not an old one, it's a legacy hand. You're not that
Oh,
old.
legacy one. Okay.
You're not that old. So do I have my class rep here?
Yes, you
Is-
do.
Yes, Anasipo. We need to decide on our test two. And our test two is on based on the work that we have covered in last semester, which is the heat exchanger. So I need you to tell me and give me a date when you are gonna write the test two on heat exchangers. And it needs to be sometime between next week and the following week.
Do you want it now?
No, I don't want it now. I want you to discuss among your colleagues and find out what is when you can do that and let me know. So either next week or the following week, and I would have it during our class period, meaning we have 2 Fridays. So the first Friday is the 18th or the 25th, one of the two. So between 18th and 25, you need to decide when you're gonna write. And the second test for transfer process is only on heat exchanger that we have done last semester already. Is it clear to you, Asipo?
Yes, sir.
All right, so you're gonna discuss with your colleague and you're gonna let me know, okay? All right. So guys, Lifa, do you wanna say something?
Yes,
Yes, Lifa.
sorry, sir, on the issue of test tools, is it
Yeah.
possible if we can have a recap of heat exchangers before we can write test two?
Oh, that's gonna take us long. Heat exchanger was long. Or maybe
More
what
like
we
it's
can do, we
something
can
like a
have
summary,
maybe we
sir.
can have a tutorial session.
Yeah.
So when do you want the tutorial session? Because we only have 1 day a week lecture for transfer process.
We can start next week since you said between next week and the 25th, sir.
Yes, but now hear me out. If I use the next week Friday to give you a recap on transfer process on the heat exchanger work, then the 25th you're writing a test. That means I'm missing out 2 weeks already for the new lectures. Remember, I only see you 1 week, one day, one lecture a week.
Or you can just upload the tutorial then, sir. Then we'll
Okay,
do
fine.
it ourselves.
I will upload tutorials. Yes. Yes, Anasipo.
So if you're available on Thursdays, we have an open day after we are free after quarter to 11 the entire day. If it's possible that you're free, you can.
Thursday.
Yes,
Okay,
if
so
everyone is fine with that.
no, Thursday I'm not free because Thursday I have lecture for my honor student from 10:45 onwards, 10:45 to 1. Because I lecture my honor students on Thursday.
And after one,
After 1, I have departmental meeting on Thursday. So that means from
Oh.
10:45 to 4 o'clock, I am busy, Miss William.
oh, okay, so thank you.
But what I will do, I will draw up a tutorial and I will post the tutorial with the memo together, right? Is that going to work? That you guys, that you can work on, and your test 2 will be something similar to the tutorial that you will see. Right. And the only for test, so when I mark your test 1, I am honestly saying that I was really disheartened. I was sad to see the marks because I don't believe the test 1 was that difficult. I think Miss Ali, Lifa, and a couple of other kids, you did well, and the rest didn't do well at all. I don't know what went wrong. What went wrong, guys? That is the work that was asked was not something new. I have done these problems with you in the class. I just asked it in different wordings. That's all I did. But that was the exact same questions that I've asked. Yes, Mr. De Villiers?
Sir,
Yes. Yes.
just by looking at this, I don't think it's more the difficult is more like trying to doing this transfer to some of us is quite a new thing.
Okay.
It's just maybe some of us just were starting to adjust to the level of the questions.
But as you move on from year 2 to year 3, the levels will also move with you. So you need to make sure that you move at a rapid speed. Otherwise, you're not going to do well. You're going to just be, fall behind. Do you understand what I'm saying?
Yes, sir. But I did find the test quite fine. I did pass it, but
No, that's good. I'm saying that we are like 70 in the class. If 10 of you do well and the 60 doesn't do well, it's not, maybe the 10 that did well is good for you, but it's not good for the class. It's not good for the for me also, because then it shows that 60 people are failing. What are we doing wrong?
That's good point, sir. Good
But
point.
then I cannot pinpoint that why I have people in my class that scores 100% for the same test where other people are struggling. I don't know how to pinpoint on that. If it was everybody, I would have understood. But then I get people that scores 100%. Remember, for test 1, I removed question 2, right? So that means there was out of 3 questions, I marked only 2 questions, and I also gave bonus mark for those who did that. Still, I was shocked when I saw the marks. I mean, that was actually very shocking to me. But I hope remember, there is only 4 assessment in this test. The first one is done. The second one you're going to do now. Then you're going to do another third test and a fourth assignment, most probably. Then it's FISA. So it's not like that you have a lot of options. So you need to do well, actually. So it's high time you guys, pull up your socks and get ready to run. Otherwise, you me. Because the syllabus is huge. The syllabus is huge for this course. I mean, the first 6 months you only spend on heat transfer. Now you're going to spend on mass transfer, and the exam going to be everything together. Can you imagine how difficult it is going to be?
No,
So,
no. But we gotta manage. You have to manage.
good. I'm hoping and counting on that you guys manage, and I wish you all the best, and I really want all of you to pass, get out of the system, and make a mark in this earth. All right, guys. I will make the tutorial and I'll post it. And Miss Wellem, please, I need the date from you. So you can WhatsApp me personally or you can email me. You have my WhatsApp number, right?
No, I
Anasipo,
do not, sir.
you come again?
No, I do not have your number.
Oh, but you have this.
Yes.
So just email me once you have made a decision. You're going to write on the 18th or 25th, okay?
Okay, sir.
All right. Guys, enjoy the weekend. No, don't enjoy too much. Go study. Bye-bye. Bye. Bye.